Yeah, good afternoon, everybody. Today's lecture is going to be 100% on the chalkboard, so if you can't read what I'm writing up here, feel free to move closer to the front. I'm also hoping for a highly interactive lecture, so I'm just going to ask like 100 questions. Feel free to raise your hand or just shout out answers. Let's make this as interactive as possible. So today we're going, and also feel free to ask questions at any point. Today we're going to talk about three topics that come up often in real-world machine learning tasks: class imbalance, outliers, and distribution shift. So for any of you who took an intro machine learning course like 6036 here at MIT, can you tell me if you covered any of these topics and to what degree you covered them in that course? Raise your hand if you've taken an intro machine learning class, either here or somewhere else. Okay, I'm just gonna pick on you in the back. Okay, so you covered domain shift, but not the other topics too much. Okay, awesome. Yeah, so I think these topics are often not covered in these introductory machine learning courses, and yet I'd say that at least one and often multiple of these come up in almost every real-world machine learning task that you might work on. So I think they're really interesting and important. And so first we'll be talking about class imbalance. Class imbalance is when you're working with a machine learning classification task, either binary classification or multi-class classification, where you have data points and you want to label them as one of a number of classes. And you have the property in your data set and in the deployment setting that the prevalence of the different classes is really different relative to the other classes. So does anybody have any examples of imbalanced classification tasks that you can come up with? Sorry, what? What prize winner at MIT? Nobel Prize winner. So how would you frame that as a machine learning classification task? Determining whether somebody is a Nobel Prize winner based on their research contributions or something like that? I think you could frame it as an imbalanced classification problem, but yeah, any other ideas? Yeah. Okay, so yeah, that's an interesting point that there have been issues in the past where people have deployed image classification models where they classified, say, dark-skinned people as gorillas because that was present in the data set. I think that's a little bit more closely related to distribution shift, which we'll be talking about a little bit later. So we'll revisit that one. And any other ideas? All right, I'll give you one and then you can try to come up with two more. One classic one is fraud detection in credit cards. So credit card processing networks have incredible transaction volume. I don't know the number off the top of my head, but it's like billions of transactions a day or something huge like that. But among all these transactions, fraud only makes up like 0.2% of the overall transactions. So the distribution looks like this. Fraud 0.2%, not fraud 99.8%. That's just what the transactions are like. And so could anybody tell me what might be challenging about training a machine learning model, which is absolutely what these companies do, right? That's the only way we can solve this problem. What might be challenging in training a machine learning model on a data set that looks like this? Yeah. Yeah, exactly. Like if your metric you're using to evaluate your model is, say, accuracy, like super standard, right? Like if you just had to pick one go-to metric, accuracy is a good one. And a model that just always ignores the data and just predicts not fraud would be 99.8% accurate, like really good, right? So you can already see how class imbalance can be a tricky issue in real-world ML tasks. So let's try to, can we come up with one or two more real-world examples? Now that we have this one to go off of. Medical imaging, yeah. So I think especially for, say, like preventative diagnostics, like say you're just screening everybody in the population to see if they have a certain rare disease or something, yeah, the vast majority of people are not going to have that issue, right? So then training a machine learning model might be hard because your model might just predict, yeah, nobody has the issue. And it's going to be highly accurate and yet very useless, right? Can we get one more? Yeah. Yeah, spam classification. Yeah, so I actually don't know off the top of my head what the prevalence is of spam versus not spam, but my guess would be that the vast majority of email is spam, and the spam classifiers have gotten pretty decent at filtering it out, so you all don't see too much of it in your inbox. Awesome. All right, so any questions so far? Is the problem clear? Like, what is class imbalance? And I think all the things we talked about here, yeah, credit card fraud, medical imaging, spam classification, these are all binary classification tasks. The same thing can happen in a multi-class setting. It's just analogous. You can have imbalance between multiple classes. And so, yeah, as we touched upon earlier with that credit card fraud detection example, one of the main things you have to do when working with this type of a problem is come up with a good evaluation metric, because just the standard, like, oh, let's just use accuracy and then go from there, doesn't really work well. Because, yeah, your evaluation metric is going to inform your choice of loss function or whatever you use to train your machine learning model. And then, yeah, you might do well on your evaluation metric if you choose some very basic one like accuracy, and yet that might not actually be what you want from the final model you get. And so, unfortunately, there's no simple answer I can give you here. There's no one-size-fits-all evaluation metric that works across all the different imbalanced class tasks you might encounter, because it really depends on like the particular domain and what kinds of failures you can tolerate versus, yeah, which ones you don't want to tolerate. And so, yeah, this can get pretty fancy. There are lots of different metrics you might come up with. So let's just talk about a couple basic ones just to see what the different choices look like and how, yeah, one choice might be better than another in a particular setting. Okay, so some of you have taken a machine learning class. Can anybody tell me what precision is? Either the mathematical definition or a more just intuitive English language definition? It's a commonly used metric used to evaluate machine learning models in the binary classification setting. Raise your hands if you've heard this term before. Okay, a couple of you, nice. Nobody wants to define it for, okay, great. It's less about, this is all like deterministic. The model given a particular data point will give a certain answer. So it's, but okay, so I think mathematically, when we think about binary classification, we have some positively labeled data points and some negatively labeled data points. And then when we classify these things, we might make mistakes. So we can have true positives, true negatives, false negatives, right? Those are the 4 possible outcomes. And so mathematically, the way we define precision is the true positive rate over the number of true positives divided by the number of true positives plus false positives. And a little bit more informally, so your classifier is going to predict positive, like this is fraud. Let's say this is the positive class and this is the negative class. It'll predict positive for some of the examples. And precision measures how many of the selected or how many of the things that the classifier predicts as positive are actually positive among all the things that were predicted as positive. So true positives over true positives plus false positives. There's another metric that's commonly used called recall. Does anybody know what this one is? Closely related to this one. You could probably guess. But this one is the number of true positives divided by the number of true positives plus false negatives. And so in plain English terms, this is how many relevant examples are selected. So there's a bunch of things that have the true label positive, and how many of those do we successfully find? So yeah, both super standard, both in just standard machine learning classification, and then we can also think about them in the class imbalance setting. And to get a better intuition for each one of these, why don't we try to come up with an example of a machine learning task where precision is a good evaluation metric to use, and another one where recall is a good evaluation metric to use. So can anybody think of a situation where we want high precision? So all the things that are flagged or that the classifier says are positive, most of them, or high fraction of them, are indeed positive. And where recall is less important, like it's okay if there's some things that are actually positive, but they're missed by the classifier. So when would we want to kind of error in that direction? Yeah. Yeah, that's a great one. So a good example for recall might be disease detection. And do you want to explain your thought process for why this is a better metric than this? Let's take, say, like COVID detection as an example there. Yeah, exactly. Mm-hmm. Yeah. So you don't want to miss any positives. So absolutely, like if you think of what happens in each of those scenarios, like, okay, suppose you diagnose somebody as positive when they're actually not sick. Well, okay, they'll stay home for a couple of days, like no big deal. But if you miss a positive, then they're going to like go into their workplace or go into their lab and then get everybody else sick, right? So much better to err in that direction. So that's a great example for recall. What about precision? Any ideas there? Okay, so I'll give you one here. So these days people train machine learning models to automatically find bugs in code, in computer code. So you might have a model that will, say, point to specific parts of your code base and be like, oh, like this looks suspicious, like maybe there's something wrong here. And with the current state of that technology, we can't really expect it to find all possible bugs. It's like too hard to reason about code right now for automated tools. And so these are, bug finding tools and not tools to like prove your code correct or anything like that. And so for these tools, we really want high precision, because whenever these tools flag an issue, like some developer has to go and look at that piece of code and like reason about it, think about whether it's actually a bug or not, and fix it. And if the automated reasoning tool just flags a whole bunch of examples that are kind of bogus, it wastes a lot of time. And so here, in that setting, you really want high precision. So automated bug finding is one example there. Any questions so far? Hopefully this gives you a little bit of a flavor of how you might choose different evaluation metrics for different problems, and that's especially relevant in this class imbalance setting. There are some fancier evaluation metrics as well. Maybe you've heard of F-score, which is the harmonic mean of precision and recall. So maybe you want to balance precision and recall. There's this fancier thing called F-beta score, which allows you to decide how to trade off between those two. So there's this, it's a metric that's parameterized by this parameter beta, and it's defined as this quantity here. And it kind of lets you smoothly trade off between precision and recall. So here, if you select beta equals 1, this basically corresponds to the F-score, which is the harmonic mean of precision and recall. If you have beta bigger than 1, then that emphasizes recall more than precision. And on the other side, if you have beta smaller than 1, it emphasizes precision over recall. Okay, so first step in dealing with a class imbalance problem is defining an evaluation metric. You have to start there. And then once you have that, then you can train a model and see, is it any good or not, given your metric, right? So then on the model training side, yeah, you have to do something special. You can't just apply kind of the standard approach you might for like a normal classification problem, because otherwise it's likely that you'll end up with a model that's not very good on your evaluation metric, right? Like we talked about in the fraud classification case, you'll probably just get a model that predicts not fraud all the time. It's not very useful. So what do you do in the model training process to get a model that does well on your evaluation metric and handles this class imbalance? There are a bunch of pretty intuitive things you can do. So actually, yeah, I'll open it up to you all and see if anybody can suggest strategies that might be useful in these kinds of settings. Yeah. Yeah, so one idea is oversampling. Right, just when training your model, make extra copies of the class that has fewer examples so that there are some more examples, and then as a result, your model is going to do a little bit better on predicting that class. Any other ideas? Yeah. Yeah, so that's a good question. The question is, if you do oversampling, do you need to be worried about data leakage? And yeah, at a high level, in general, you need to be worried about data leakage and make sure that you're not having the same example in the train and test set. So the way you do this with class imbalance is you're going to do a stratified split of your data set up front. So you split up into your train and test set. Make sure you don't just like randomly split it and have different proportions of the different classes, but preserve the relative distributions you had in your original large data set when you do your train test split. And then anything interesting you do to better train on the imbalanced data, like all of this you do only with the train set. So you would never include a test point in this oversampling, just the train examples. Yeah, that's true. Yeah, so you would have a duplicate in your train set. And that's totally fine, right? In some scenarios, it can give you bad results, but it's one technique you can use, and sometimes it works. Is that another hand? Yeah. Any other ideas for how we could deal with class imbalance? Yeah. 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 Yeah, closely related to oversampling. Here, one way to think about this is you change your loss function to have individual weights for individual data points. So you have your per example loss, and then you weight things differently, and then you can overweight the minority class. And some machine learning algorithms let you supply just per sample weights, and it kind of fits in nicely into that paradigm. Any other ideas? I guess nobody guessed this one, but closely related to oversampling is undersampling. And it turns out people found in practice that oversampling can be a little bit more unstable, and in some scenarios, undersampling can actually outperform. So you actually just throw away some of your examples of your majority class to have a closer to balanced data set. Now, the tricky thing is, like in that fraud example, super imbalanced data set, right? You'd be throwing away tons and tons of those not fraud examples to try to get closer to a balanced data set. And so it can be a little bit tricky. And then the lecture notes talk about a couple more slightly more advanced techniques. So feel free to refer to those if you're interested. But these three should give you some idea of some of the techniques people use, and that can be surprisingly effective at dealing with class imbalance. Any questions so far before we move on to the next topic of outliers? Cool. Can anybody tell me what an outlier is? I'm sure everybody's heard this term before. You don't have to have a precise formal definition, just a kind of intuitive. What do you think of when you think outlier? Yeah. Yeah, so something at the, like a data point at the tail end of your distribution. Another even more informal definition is data points that just differ significantly from the other data points. And I haven't precisely or formally specified what differ significantly means, but as an intuitive definition, it's pretty good. And so in picture form, suppose I have this data set. I'm actually just showing features here. So in feature space, we might have a feature x1 and x2. I'm going to draw a bunch of points in here. And when I draw this picture and I tell you find the outlier, can you tell me which one it is? Yeah, it's this data point up here, right? Like humans are surprisingly good at looking at various types of data sets and picking out the things that look different from the rest. And so in this class, we're all about systematic approaches to these data problems, right? So we're not just going to say, like, oh, the way you find outliers is look through a billion examples in your data set and just pick out the ones that are bad. We want to come up with algorithms to automatically identify these. So we'll talk a little bit about that. But before we talk about algorithmic ways to identify outliers, can anybody tell me why finding outliers might be helpful? Like what problems would they cause? Why do we want to find them? And what you might do once you find an outlier or find outliers in your data? Yeah.
If you have outliers, it may skew a lot of your distributions in a way that it becomes very difficult for your model to perform well on, being able to like use. And if you find outliers, it may also be helpful for cleaning up your data up if you choose to remove them because they're just not representative, maybe due to some data entry error or a number of other factors, just may improve performance of the model, as well as maybe alert you to problems.
Yeah, exactly. So outliers can harm machine learning model performance. That's one of the main reasons we might want to identify them. And then if they're indeed, say, a result of bad data entry, we probably just want to get rid of them. And if there's something else going on, we'll at least want to think deeply about what's going on and maybe address it in some way. So can anybody come up with some examples of causes for outliers, like why we might end up with outliers in a data set? So you already named one, bad data entry. Maybe people are, say, labeling a large data set that consists of a bunch of images, and after they've labeled 1,000 of them, like they start making mistakes because they're tired. What other causes might there be? Yeah. Yeah. Mm-hmm. Yeah, so we'll call that rare or unusual examples. And so these aren't like erroneous data points that you just want to throw away, but they're still outliers in some sense. Maybe we want to handle them differently. Yeah. Yeah, so maybe something in the data itself has changed. Do you have any concrete examples of that? Yeah, so we'll talk a little bit more about that in this next part of distribution shift, like something in your data changes. So a little bit more closely related to that than outliers. Yeah. Yeah, that's a great one. Let's. Mm-hmm. So let's call it, say, like a bad sensor readings is one example. Yeah, just your measurement instrument is damaged or flaky or something, and you get some funny data that's, yeah, like bogus, and it looks very different than the rest of the data. Great, and so we're going to talk about how, like, algorithmic means through which we can identify outliers. And then what exactly you do with the outliers depends a little bit on what type of outlier they are. Like if it's bad data entry, say like a mislabeled example, and that's why it's an outlier, maybe you just want to fix it. If it's a bad sensor reading, maybe unclear that you can fix it. Like you measured something at some point in time and it's just bogus, like you can't go back in time and get the real reading. Maybe just throw this away. For rare or unusual examples, you might actually want to handle it differently. Like those are actually super valuable data points because they're like real, they're not buggy or anything like that. And you actually might want to make sure that your machine learning model handles them correctly, like that stoplight example we saw in one of the previous lectures. Any questions so far? And one way we'll break down or categorize outlier detection into one of two categories is outlier detection versus anomaly detection. Both broadly related to this problem of outliers, but slightly different problem settings. So in outlier detection, we have a bunch of data, and we want to find data that looks different from the rest. So this is an example of an outlier detection problem. Whereas in anomaly detection, the setting is slightly different. We're given a data set with a bunch of examples in it, and then given a new data point, we want to determine if this data point came from this distribution or not. So does everybody see how these are two slightly different problems? Right? Here I'm not told like what is in distribution, whereas here I'm given what is in distribution, and then given a new data point, I'm going to figure out did it come from this data distribution or not. And these are closely related. Like for example, suppose you had an algorithm for outlier detection, and then I gave you an anomaly detection task. How could you use the outlier detection algorithm to solve your anomaly detection problem? Does anybody have any ideas? There's a pretty simple transformation between the two. So say you have an algorithm where you can just give it a bunch of data points, and it'll tell you these subset of data points look very different than the rest. Now I give you a problem where I give you a bunch of data points, and I tell you this is all my data distribution, and then I give you one other data point, and I ask you the question, does this belong to this distribution or not? How can I cast this as an instance of an outlier detection problem? Yeah. Yeah, exactly. You just combine all these data points with this one, give it to the outlier detection algorithm, see what it flags as being an outlier, and then if this data point happens to be one of the ones that's flagged, then it's anomalous, otherwise it's not. And then to make this difference really concrete, can we come up with an example of each of these, as some real-world example of a task that involves either outlier detection or anomaly detection? So I'll give you one for outlier detection. Suppose I just have an image data set, like an image classification data set. Maybe some of the images in there are just bad, like they're blurry or something, they're just kind of bogus. And I have this big data set, and I just want to find these bad examples and throw them out. That could be framed as an outlier detection problem, like the blurry images are outliers among the other ones. Notice there, I don't have like here are good images, now given a new image, is it good or not? It's just I have a big collection of images and I want to find the bad ones and throw them out. Any ideas for an anomaly detection example? Plagiarism. Okay, that's an interesting one. So you might have, say, a bunch of homework assignments and a professor's graded all of them, and they've thought deeply about it and determined like, okay, like none of these students plagiarized. And then the next year, the professor doesn't want to think too deeply about this and instead wants to use a machine learning algorithm to figure out, like, oh, given another student's submission, does it look like plagiarism or not? Like, does it belong to the non-plagiarism distribution or not? That's a good one. Any other ideas? Yeah.
So like the military uses Outlier detection in two ways. One is the amount of signals that are attacking, like the number of IP addresses that are getting on a private network. And just, you have like a table with normal, and you have spikes. And the second one is ocean. You have a bunch of images that are being in the ocean. And then if the ocean has like a shit on it, or anything weird, that's an asset. And then also oceanography, that is like right up there, otherwise it's just all the same. Ocean.
No. Yeah. Yeah. Yeah, that's a good one. So maybe you don't have a priori, like you have a bunch of examples of defects and examples of non-defects. You just have like, okay, we produce a bunch of items, they all look good, and now I want to start monitoring for anomalies in the future. All I have is the good examples. So yeah, that's a good example of anomaly detection. Cool. Any questions about that before we move on? All right, so now we're going to look at a bunch of algorithms we can use for identifying outliers in data. And so we'll start with some really simple ones and then look at some slightly fancier ones that work surprisingly well in practice. So just to get us warmed up, we're going to consider a really simple application domain where our data points are just real valued numbers, right? So super like one-dimensional, just like 3 or 4.5. So this first one we'll look at just to get us warmed up is a method that was proposed in like 1977 or something like that, called by a statistician called Tukey. And the method is as follows. So we're just thinking about one-dimensional data points right now. So we can just plot them along the real line. And here I'll mark them as little X's on here. So you have some data points along this line. And one method you can use, what this method says, is find the first quartile and the third quartile. So like 25% of the data is here, 50% of the data is here, 25% of the data is here. Define this as the interquartile range, and then look at these as thresholds. So take 1.5 times this interquartile range and increase our like bounds by that much on each side, and then say like this is what's considered in distribution. So if we have a data point over here, we'll flag that as an outlier, but all the data points here are considered not outliers. So there's no like scientific basis where we can prove that like this finds outliers in a data set, yet it's surprisingly effective in simple settings. So just getting us warmed up here. Any questions about that one? I think in lecture 1 or 2, somebody mentioned z-score. So that's another technique you can use for identifying outliers. You can give a score to each data point, and then the higher the score, the more likely it is that it's an outlier, and you can find a cutoff and define everything above that as an outlier. So recall that the z-score of a particular data point is that data point's value minus the mean over the standard deviation. And so if you have normally distributed data, for example, you'll say like, okay, you might pick some threshold, like, okay, we're going to look 3 standard deviations on either side and define anything at these tails of the distribution to be an outlier. Yet another simple method. Any questions about that one? All right, these are too simple. Nobody's excited yet. Okay, we're going to look at some slightly fancier ones that are actually pretty neat. So this next one we're going to talk about is called isolation forest. And it's a pretty neat technique. It's pretty simple. So actually, if you want to, you can take today's lab assignment and implement this yourself. Like actually just write the algorithm from scratch yourself. And intuitively, the way this method works is it's related to decision trees. And hopefully most of you have heard about decision trees before, and if not, I'll explain it briefly. But intuitively, the way this method works is it creates a random decision tree for the data. And then the score associated with each data point is like how deep you need to go in the decision tree to isolate that data point from all the other data points, right? And so if a data point is like really far off from the rest of the data, you probably don't need to go very deep in the decision tree to isolate it, right? But if there are a bunch of data points all together, so then any individual data point there is not that far off from the others, well, then it's less likely to be an outlier, and you need to go deeper into the tree to actually isolate it from the rest of the data. And so this one's much easier to understand when I draw it out in picture form. So here we're going to look at yet another data set. This one's a two-dimensional data set now. And I'm going to draw data points as a bunch of dots. And then we're going to run this isolation forest algorithm on here. Also, just looking at this data, if I told you like, there's one outlier in this data, can you find it? You can always point to this, right? But we want to find these sorts of things algorithmically. And so the way isolation forest works is it's just going to create a random decision tree for this data. So we might start off and pick a random feature. So maybe we randomly pick the X2 feature, and we randomly pick some cutoff. Like maybe we pick right here is the cutoff. And so here's the first node in our decision tree. So we'll start building up our decision tree, and this first node will be like, is X2 less than, I'm going to say this is like 1, 0. Is X2 less than 0.4? Then we have the two branches here, right? And so far, we haven't isolated any data point. So we have to keep going until every data point's isolated. So I'm not going to draw out the whole tree, but I'll go a couple levels deeper. So maybe in this left branch now, we'll randomly pick X1 and pick like this as a cutoff. So we'll have, is X1 less than 0.2 or something like that, and continue building up this decision tree. Maybe in this branch of the decision tree, we'll also pick X1 randomly as a feature and randomly pick this as a cutoff. So note that, yeah, like we don't have to pick the same cutoffs or same features in different parts of the decision tree. It's all just randomized. So in this branch of the decision tree, we might have like X1 is less than 0.5. And notice here, we've already isolated this one data point, right? So I only needed to go 2 levels deep in the decision tree in order to isolate this data point. Whereas for all the other data points, I have to keep going. Like I might, okay, on this this branch here, I might say split the tree here, and I'll have a X2 is less than 0.7 and so on. And so I'll keep recursively splitting up this space, and then associated with each data point, I will have a depth in my tree. Yeah?
So just to make sure I understand, you're saying that each of these splits is formed completely randomly?
Mm-hmm. Yeah. Pick a random feature, pick a random cutoff. Yeah. Yeah, so the question is, since it's randomized, do you have to run this multiple times? Yeah, I think you'll get a better estimate if you run this multiple times. There's a link in the lecture notes, and it links to the original research paper that proposed it. So a lot more details and some like analysis of bounds and stuff are in there. Any more questions? Yeah, so kind of neat method, right? Yeah.
You might be talking about it later, but I'm curious how you contrast these 3 methods and whether there's a time that you use one over another.
Yeah, so the question is, how do you contrast these 3 methods, and is there a time you'd use one over another? I think ideally, if you can set up some sort of experiment on your data where you actually know for some subset of your data, then you can just benchmark these different algorithms. Otherwise, you want to look at other people's benchmarks on like kind of similar data and see what works better. So some of these things, like this is so simple, it likely just doesn't apply to your data, right? Like I think isolation forest is something that's a little bit more general. The next one we'll talk about is also more general, and yeah, those are the more likely candidates. Any other questions? Cool. So we'll talk about 2 more algorithms before we move on to distribution shift. So this next one is another, pretty useful method. Yeah, I think some of these ones, like you're not going to use this on your data set because it probably just doesn't apply. Whereas these, like this next one I'm going to talk about, almost certainly applies to your data. Like lots of people use it in practice. Super useful. Works quite well. This one's also easiest to explain through a picture. So hopefully most of you have heard of k-nearest neighbors, right? Like take a data point, look at its k-nearest neighbors in the feature space. And it turns out that you can create a metric based on that that's surprisingly helpful for identifying outliers. And this is also super intuitive. If I asked you to come up with this kind of an algorithm, to come up with some algorithm for identifying outliers on your own, maybe you'd be able to come up with this on your own. So one thing you might do is look at k-nearest neighbors of a data point. In this picture, I'm just going to pick k equals 3. And then say, if I want to give a score for a particular data point, like I want to score this data point, what I'll do is I'll find its 3 nearest neighbors and compute the average distance to them, right? And for this data point, for example, that'll be small because there are a bunch of other data points that look like it. Whereas for this data point, this is going to be large, right? Like its 3 nearest neighbors or something like this. So the KNN distance here is very large, whereas here it's very small. And so you can come up with scores for outliers based on this technique. So what if I had, going back to one of my earlier examples, what if I had this image data set and I want to identify, say, like weird images in there? Could I just directly apply KNN distance? Like what would I do there? What do you think would happen? Like if I say directly just took the pixels in the image as the individual features and then just looked at this distance metric? It might not give the best outcome, right? Because like distance between different images in pixel space is perhaps not the best metric for comparing images. If I have, say, a data set of cats and dogs, lots of like diverse looking pictures, and then there's a couple pictures of like Curtis in there, and I want to find the ones that are anomalous, just looking at differences between pixels in this very high dimensional space is unlikely to give good results. So any ideas for what we could do there if we still wanted to use KNN distance? Yeah. Yeah, so some kind of autoencoder framework. There's another way we can use autoencoders, but yeah, one thing we could do with an autoencoder is just encode our images, right? Go from our high dimensional representation, the raw pixel values, to some lower dimensional representation where distance under some distance metric is a more meaningful comparison between data points. And so you don't have to use an autoencoder. There are other things you could use. Like for example, working in this image domain, you could take a model that's a pre-trained model that's trained on some image data set, take one of the like penultimate layers of that model, and just use that as a feature representation for your images. And then look at distances there. So this method works surprisingly well in practice. I think if you were to choose a default method, I would say embeddings plus KNN distance is a great one to use. Any other questions? And since you mentioned autoencoders, the last method I want to talk about is related to autoencoders. It's a super cool one. It's just a clever method, so I think it's cool to go over. Raise your hand if you're familiar with an autoencoder. That is. Okay, roughly half of you. I'll very briefly explain autoencoders and then talk about how they could be useful for finding outliers. So autoencoders can be used to take some input data. Let's talk about images here. Say you have a picture of like handwritten digits, like the MNIST data set. You have this 5. What autoencoders do is they're models that consist of 2 parts. One is called an encoder, the other is called a decoder. And the idea is that this encoder turns your input data, some high dimensional complicated thing, into some lower dimensional latent representation. So maybe you turn your image of a 5, it's like whatever, 700 something pixels in MNIST, into say like a 10-dimensional vector or something, right? Much smaller latent representation. And then you have a decoder that turns this back into a reconstruction of the image. And so the idea with autoencoders is that you can train this whole thing, so jointly train the encoder and decoder, get some good latent representation out, and then these things have a bunch of different uses. But one of the ways we can use this to identify outliers is leveraging this property that the autoencoders have to figure out how to compress the high dimensional input into this low dimensional latent representation. And so they kind of learn, kind of like, you can think of them as kind of modeling the data distribution as part of that. Because you can't encode, like directly encode all the values of the pixels in here. You kind of have to encode, you might imagine that the latent representation captures something like, what is the digit? And like, roughly what is the handwriting style used to write down that digit? But it can't just encode arbitrary pixel values. And so what might happen once you train an autoencoder on a data set like this, like say you train an autoencoder on MNIST, then if you pass in a handwritten digit like a 5, you might get something out that looks very similar. But if you pass in something like totally random, say I pass in the smiley face through this whole thing, I might get out something that looks totally different. You could actually try this, just train an autoencoder on MNIST and see what happens. I wouldn't be surprised if you get something that looks vaguely like a handwritten digit, because like this was designed to compress encodings of handwritten digits into a low dimensional representation. And so the way you can leverage this to identify outliers is use the reconstruction loss as a score. So what you do is you come up with some appropriate distance metric. Here, working with images, say you can even use L2 distance, like just distance between the pixels. And for in-distribution data, you'll expect this reconstruction loss to be small. Whereas for out-of-distribution data, the output will change a lot compared to the input, and the reconstruction loss will be larger. This is a kind of neat method leveraging autoencoders. Yeah.
I understand this is assuming there's no label, but if there's label, how does the instruction loss different than the regular loss of the model? Yeah, I know traveling.
Okay, so the question is, how is the reconstruction loss different from the loss that's used to train the autoencoder? Is that the question?
If you have a label. This is kind of in the loss based on the original value, but regular loss is kind of the loss based on the label itself. So I just wondering if there's any reference to those two types of losses.
Yeah, so well, you could even train an autoencoder without labeled data, right? That's a totally fine way to train this kind of a model. But yes, if you have like a
Let's just use, for example, if I have a model trained, it's a regular model, and I do have a label, and I just fill it with the data and all those that have high loss, would that be a potential candidate of outlier?
yeah, I think so. Any other questions about this? Cool. And so I think today I don't have enough time to give a proper treatment of distribution shift, so we'll just let that overflow into one of the future lectures. There's a cool lab assignment for today's lecture. We collected a data set, created a data set for you consisting of a bunch of pictures of dogs with some outliers in there. And then the assignment is, explore various methods, including some of the ones we talked about, in order to automatically identify outliers in there. We have a bunch of scaffolding set up for automatically we have the ground truth because we created the data set, right? So we have some code we've provided for automatically benchmarking the different outlier methods. So you can experiment with that and see what works and what doesn't on that data set. So yeah, I would encourage you to experiment with that lab assignment. And in the next lecture, so for the next two lectures, we have Jonas teaching. The next lecture is going to be about data set curation on Monday. It's a very cool lecture. The focus will be on multi-annotator data sets. So say you have like a big image data set and you want to label it. One of the common ways to do that is just farm that out to say like mechanical Turk workers. You have a bunch of humans label your data points, but humans make mistakes. And so one of the ways you deal with that is you have multiple humans label your data points. But even then, like, okay, now we have one person who says this is a cat, one person who says this is a dog, and another person who says this is a cat. Like, how do you combine all that into the final labels for your data point? How do you do that in the way that gives you the best quality and also like identify interesting properties, like who are your best annotators and worst annotators and things like that. So we'll be going deep into the multi-annotator setting and covering some pretty cool algorithms for that on Monday. Well, any final questions? Yeah. Outlier detection methods for time series. Not off the top of my head, but I can talk to you after class. Any other questions? Cool. Well, we will see you all on Monday. Have a good weekend.